Obviously, well, not obviously, but one of the things you need to understand about pain is it's a very complex phenomenon. There's a very big cognitive component to pain perception. One of the big cognitive components of pain perception is expectation. Um, the big example of expectation is placebos. If I fool you well enough with a good placebo, I can give you a sugar pill that I've convinced you is a very powerful narcotic. And believe it or not, a good number, 40, 30, 40, even 50% of people will experience pain relief from that sugar pill if a doctor tells them it is a very powerful narcotic. Uh, Also, when patients are told what to expect, they request less pain medication. They leave the hospital earlier. So if you just roll a patient into surgery and just don't tell them anything, when they come out of their surgery, they're going to be in a lot of pain and they're not going to know what's going on, so they're going to request more pain medication. But if you tell them ahead of time that yes, this is a very sensitive procedure, it's going to hurt pretty bad, it turns out that they're able that in general they request less medication, less pain medication, primarily because their cognitive component is dealing with the pain better. Shifting attention using things like virtual reality technology can also reduce pain perception. So if I'm having you pay attention to something, uh, focusing on something, and then testing your pain perception, your pain threshold is going to be much higher when you're focused on something versus if you're not paying attention to anything else. Um, I can distract you with emotional distracting. So one of the things that we test with pain perception is how long you can put your hands in ice cold water. We measure that threshold. The dependent variable is how many seconds the subject puts their hand in cold water. Uh, if I show you positive pictures, pictures of cute kitties and families and pictures like that, you're going to be able to hold your hand in the water longer than if I show you negative pictures that disturb you, say for example. Um, there's also Derbyshire did some fairly famous investigations of hypnotic or using hypnosis to induce pain. Um, so the participants had a thermal stimulator attached to the palm of their hand, and what they did was had three conditions. One was physically induced pain, where they actually turned this little hot plate on their hand to induce pain. And then they had hypnotically induced pain, where he hypnotized them and then said, "You will feel pain." And then they had a control group where they weren't hypnotized, but they were just told, "Imagine the pain coming from this device." Um, and the really interesting thing is that the hypnotic the people that were put under hypnosis reported that they were feeling pain, and their MRI scans showed that their somatosensory areas were lighting up as if they were perceiving the pain, whereas that didn't happen with the people that were told to imagine the pain. So here's an example, right? Notice that the physically induced pain, these areas of the brain light up, and notice here in these pictures here that in the hypnotically produced pain, that very similar areas are lighting up there as well, telling us that uh, the somatosensory areas here telling us that these people are actually perceiving pain. So this is a video that I will put in the area for you so you can watch this video. There's many different areas of the brain that process pain information. So beneath the cortex, we have the hypothalamus, which is the area that I studied when I was doing research on pain perception, the limbic system, and the thalamus. The thalamus projects to the cortical areas, including the sensory S1 area, also to a part of the cortex known as the insula, and the anterior cingulate and prefrontal cortices. So all of these different areas receive pain information. The prefrontal cortex is a high cognitive area, and the insula and the anterior cingulate are related to learning and emotion. So all of these areas work together to cognitively process pain. All of these cortical areas together are referred to as the pain matrix because they all receive information at the same time for a particular pain stimulus. And here they are. Here's the prefrontal cortex. The thalamus is here. S1, the insula, the amygdala, and the hippocampus. All of these different areas receive pain information and process it in different ways. Um, so Hofauer did a study where patients were presented with potentially painful stimuli, and they were then asked to rate the subjective pain intensity and to rate how unpleasant the pain was. So what they did was they measured their brain activity and they placed their hands into very hot water, and then they hypnotized them to increase or decrease the sensations and the suffering that they were going through. When they were hypnotized, the suggestions to change the subjective intensity led to changes in the ratings and the activity. So, in other words, when the subjects were told that the water's really, really getting hotter and hotter and hotter, they rated the water as hotter and hotter and hotter, and also they saw corresponding activity in area S1. But when the suggestions to change the unpleasantness of pain the suggestions to change the unpleasantness of the pain did not affect the subjective ratings, but it did change the ratings of unpleasantness. So, in other words, we had this separation between the actual perception of the feeling, the intensity of the stimulus, and how unpleasant it was. We were able to separate those two things. And it's an interaction, I guess. So this would be here, right? Um, so the suggestion to decrease intensity and increase intensity led to an increase in intensity and unpleasantness. I'm sorry, the suggestion to increase intensity when they're hypnotized led to an actual increase in intensity, perceived intensity, as well as perceived unpleasantness. And similarly, the suggestion to decrease the intensity of the stimulus led to a reduction in the decrease of intensity and a reduction in decrease in unpleasantness, right? Which you would expect, right? That makes sense. However, this is the cool part right here. So then we say decrease the unpleasantness, right? So you're not suffering as much or you're suffering even more. Notice it didn't really have anything, it didn't change the intensity. But it changed the unpleasantness. When we told them to decrease the unpleasantness did decrease, but the intensity or the unpleasantness went down, but the intensity stayed the same. Right? The intensity stayed the same, but when we told a decrease, right? Um, Unpleasantness went down, but intensity stayed about the same. And this is really interesting because it tells us that we have it tells us that we have separate mechanisms that regulate the cognitive subjective feeling of unpleasantness versus the actual perception of the intensity of the stimulus. So I could theoretically, right? I could theoretically for example, you read these stories about these war heroes that um, that won these medals of honor, and they had these horrible injuries. Like Roy Benavidez, right? If you read his Medal of Honor citation, you'll see he was shot multiple times, and his guts were hanging out basically, as he rescued all these guys and put them in a helicopter. So the intensity of that pain was probably pretty intense, obviously, but the unpleasantness was lowered um, such that he was able to do what he had to do. So we can separate these two aspects of pain, I should say. Opioids. So it's long been known, ever since we started, eating poppies and whatnot, that opioids are very effective painkiller. Matter of fact, they're the best painkiller we have. Things like morphine, uh, and all the synthetic morphines that are out there nowadays, all the synthetic opioids that you take nowadays, are very powerful painkillers, and of course they're also highly addictive, unfortunately. We also have opioids in our brains that are naturally part of our brains, and these opioids have been referred to as endorphins, and they're used as a neurotransmitter. And it turns out that these endorphins do, in fact, reduce pain. Um, if I were to inject a rat with naloxone, which is a drug that blocks endorphin receptors, I will induce more pain because the endorphins aren't able to work. Naloxone also decreases the effectiveness of placebos. So if I trick you with a placebo and say this is a very powerful opioid, and you take it and you experience pain relief, I can block that pain relief with naloxone, which suggests that that placebo effect is maybe due to the release of endorphins. We're also able to measure endorphin levels in living people, and people that release more endorphins can withstand higher pain levels. Um, so here, another powerful opioid is heroin, right? That's a very powerful opioid, of course, very addictive. So here's an opioid site. It's blocked by naloxone, and I can do that. One of the drugs that you give people that have had a heroin overdose is naloxone. You give them naloxone and it blocks the opioids, and that way the heroin cannot bind to the opiate sites anymore. If I release endorphins, those endorphins are released and go to the opioid sites and bind to that and reduce the perception of pain. And similarly, naloxone, given again here, blocks the binding of endorphins to the receptor site, just the way it prevented the binding of heroin to the receptor site. This is some cute data from Benedetti, reported in 1999, and it's a very straightforward study. Essentially, what happened was painful stimulus was applied to either the left hand or the right hand, or the left foot and the right foot. And these are indicated by LH, RH, LF, RF. Left hand, left foot, right foot. And the first on the first graph, A, you see the pain rating when the painful stimulus was applied, just applying it. And then in graph B, what we saw is the subjects were told that they were going to have a powerful pain relieving cream, placebo cream, placed on their left hand. And when that happened, so we put the pain relieving cream on their left hand, and we exposed them to the painful stimulus again, and lo and behold, they had a decrease in pain rating. It went from like almost 6.5 to 3, so cut in half. And then, of course, in the graph C, the subjects were told you're going to have a placebo cream put on your right hand and left foot, and then we're going to test it. And sure enough, we got the same results. We were able to decrease the pain in the right hand and the left foot where the placebo cream was placed. And notice this cream wasn't real. It was just a fake fake cream. Oh, this is interesting. So Keyser and co-workers, what they did was they looked at the effects of being touched versus watching people or objects being touched. And and they measured the brain responses to either being touched or watching people or objects being touched, and also Meyer and his coworkers had people looking at people, watching people haptically exploring things, and they found out that when people were watching this, that the somatosensory areas of their brain were being activated. Um, so Keyser in the 2004 study found that watching people being touched in certain spots activated those same areas as when they were being touched versus when objects were being touched. And Meyer noticed that when people were observing others haptically exploring objects, their visual and somatosensory areas of the brain were also activated, which tells us that we use our somatosensory system to visualize and perceive what is happening with other people. So this is some data from Keyser's experiment that we mentioned here. Um, Notice that whenever now this is, pretend you're in the experiment and you're watching these pictures, right? So you see the picture, the control picture, and the experimental picture, or the experimental picture. So in the control picture, whenever the subject was being touched, or whenever the binders were being touched, this increased the firing of activity in the somatosensory areas of the brain, S1 areas of the brain, which is really interesting because it's telling us that our ability to perceive others being touched or others what others are feeling relies on our own touch mechanisms. Notice in the bottom that we simply have an airplane wing overlapping with an aerial view of an island there, versus one that's not overlapping. And notice that did not cause a change in the activity in the somatosensory cortex, which tells us that this activity is directly related to touching objects or touching other people. So here's the somatosensory area that gets lit up whenever touching occurs, and here's the occipital cortex, which gets lit up when vision occurs. Now this is a view. This is the human brain. This is kind of a top view. We're basically looking down on somebody's head. So this would be, I guess, the left side of their head. This would be the right side of their head. Their eyeballs would be under here somewhere. Their ear would be about here. This is the back of their head. This is their forehead right here. And this would be the somatosensory area where you see the activity whenever touching is occurring. So to explore this further, right, observing touch and pain in others, right, Singer did a study where romantically involved couples were participated, right. So we got these couples that knew each other really well, and then they connected up they took the woman and put her in and measured her MRI. And then once she was in the MRI machine, they either gave her little shocks, electric shocks, or she watched while her partner was shocked. Now, notice that these are romantically involved couples, so they're people that know each other really well. And the woman is either perceiving shock herself or perceiving shock in somebody else. Either way, whether she's perceiving shock in herself or perceiving shock in somebody else, her partner, similar brain areas were activated in both conditions, namely, here it is right here, actually. Right here, right along here. So when she receives painful information, it lights up quite a bit. But even when she just watches her partner get stimulated, it lights up the same identical areas as one of the areas as that lit up when she got shocked.